you listening at home. We have almost as many of you listening at home as we do in class. So remember, the quiz is on Friday. So hopefully be ready to go. Whether you got a broke down truck or not, you'll be able to do the quiz. All right. Test and see if he's watching. All right, so let's take a look at maybe the business packet problems. Of course, we got, just quickly, again, throw this stuff up here. Parametric equations will be on there. We did the Luke Skywalker problem. We'll be doing some more review of those tomorrow. I'll throw up a couple of examples, talk very specifically about what I want you to be able to do. I want you to be able to draw a graph, be able to trace on a parametric graph, be able to show the direction of travel, be able to find horizontal, vertical velocity, slope, speed. We know these formulas, basically. Probably keep it fairly simple. I think our optimization and our related rate problems are probably tricky enough. So probably be pretty straightforward with the parametric equation ones. Just be able to use these formulas to answer some questions about, okay? Then optimization, of course, of max min, kind of like our problems today with the river, running the cable across the river, that kind of thing. Our max min kind of problems. And then, of course, our related rates, which we got into with the swimming pool problem today a little bit. The cone, the one cone problem, 23 was kind of tricky too. And 26, the swimming pool problem, both were pretty difficult, probably more so than what the quiz will be like. The quiz will be pretty straightforward, but again, you need to see these kinds of things. It's the same process that you go through, but they each have a little bit of a trick to. Well, really, the swimming pool one, there is the only thing more difficult maybe about the swimming pool problem is it's just a shape that you may struggle with, just a triangular kind of prism shape. So it's not that hard, but it's the first time you've seen it again, probably that kind of shape. So in this kind of problem, so that makes it a little trickier. But I'm probably not giving you enough credit by saying, it's too hard, you guys can't handle that. You should be offended if I say that. So anyway, so the swimming pool one we'll get to. So let's do the business packet. Any questions on either one of those? Okay, the answers were up there, obviously. So, online, if you wanted to look at those, but you got to put yourself in a position of, hey, I got to do this on my own in the quiz, so what you want to talk about either one of those at all? 21, what was the deal on 21 now? It was at, I got to remind myself here. Oh yeah, okay, we're a certain product, $40 per unit, 300 units, but if the price goes up 5, then it drops to $75, or drops $25. So again, that's where, to me, if I just show you what we did the other day, I just think the easy way, if you're not sure, make yourself a little XY thing. 300 units, $40. 275 units. What was it? A price drop 40. So it would go 45, right? I mean, like that. Goes down 25 units with a price increase of $5. So now all we have to do is a slope calculation. Now remember, your Y is the P, right? X is the number of units. So make sure you get those numbers in the right spot. Okay, but 45 minus 40, 275 minus 300. Now this might be a little different than I had set it up in the, I don't remember, but it could be a little different than I set it up on my answer sheet. But there's your slope. So your price equation is just going to be negative 1/5, and then pick one of these points. So x minus 300 plus 40. So that might be a little different than I had set it up on mine, but it's still the same. It's still the same thing. Okay. So that's how much. That's the slope, if you will. Okay, it's going to be $5 up, and they'll drop 25. So that's this slope, and then put in this point. So there's your price. So then all you have to do is take that times x. And then what is it still? Oh, they just wanted revenue, right? They just wanted revenue. So there were no costs. Okay, so that is your revenue right there then. That is your revenue. And then you're just going to maximize that to reduce it and equal to the whole thing. Okay, and then this is a lot like then this would be a lot like the old snowmobile, right? Very much the same thing. At what point do we put this across the river to make that a maximum? So, um, okay, you just have, this is 0.5, this was X, it was pretty much given to you, which was nice. So this would just be 0.5 squared plus X squared, square root of that. So take that times $8 a foot. 6 minus X on the land is cheaper, so that's $6 a foot. You add those together, that's your total cost. And then you're trying to minimize that, so do the derivative, set equal to 0. Where would, I don't think it's ever undefined. I did go a little farther with that one. Endpoints, X could be 0 if you come straight across, X would be 0. And then the most X could be was 6 if you just go, no, I'm sorry, that would be if X is 0, you go straight across the river, like so, okay? And if X is 6, you do the whole thing this way, come straight across and go the whole way there, okay? So X could be 0, X could be 6. Here's the different versions. So it looks like the minimum cost was going to be right there. And then you were supposed to plug that back in, I think, and get the cost. So you had to plug it back in. So make sure you answer the question. Okay? All right. What about the ones in the book then? 26 and 23 will do.
Just a question about the business package. So these are both like profit and cost.
Yep.
Is calculus used in like econ and finance and like monetary policy?
Yeah. 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 And to be honest though, I think if you talk to somebody in that world that did that kind of stuff, I don't think they would say they're using calculus per se. It's probably behind the scenes, you know what I mean? So they use things that behind the scenes, most of, anybody who takes that is going to take calc. But like I think I was telling you the other day, if you major in business, you're going to take probably applied calculus, which you're going to have a lot of this kind of stuff, and then it's a lot of it's used is technology, right? Then you're using computer models and you're using, things like that. You take a management class or you take, different finance classes, you're going to be using those kind of things. My son's right now he just took corporate finance, he took an investing class last semester, and they didn't use calculus per se, but the formulas and some of the stuff they were doing behind the scenes, I think had some of that, for sure.
Yeah, I asked my dad about that actually last night. He said that they don't really use calculus because it's all linear.
Right.
Algebra, they just kind of go around the calculus.
Right. A lot of stuff, and one of the things that in Calc 2 we get right up to, but we don't do, is taking more complicated functions and converting them into something easier, like polynomial type, like linear, or they're called Taylor polynomials. So you want to fit something that looks maybe like a sine or something like that. You think about one hump of a sine curve kind of looks like part of a parabola, right? Or a fourth degree that kind of does this, or a fifth degree. Well, parts of it look like kind of a sine. So you get some of these things. There's ways of fitting that to easier equations. So like you said, and if you look at we've also talked about, if you look at any curve, if you look at a small area of it, it's somewhat linear, right? So like you said, I like how you said worked around the calculus part of it. Because of technology, they can that, a lot of that's behind the scenes. Now the guy who's programming and writing it, that's coming up with these models is probably more versed in it and using that more. But the actual users of it, much like, we drive a car without being a mechanic, it's somewhat the same thing. But in your preparation, you're going to go through that and put that down. I'll have to ask Ryan more about what he's in his classes, how much that. I don't think a lot. Like I said, he took Calc 1. He's a double major. He's a major in math, so he's taken a lot of math. But as far as just in his finance classes and stuff, I think most of those can just get through Calc. Just take applied Calc. Now, with that said, as he's talked to me about other people in his class that have struggled, that have had a hard time, and have thought that the corporate finance class was really hard, and he was kind of worried about going in. That wasn't very hard at all. Well, I really think his math major and his math background helped him a lot so it wasn't as hard, so. Okay, what about the, anything, 23 and 26, I want to do those. What about the first 12 or 16? You want to see, was one of those a cone? 16. Let's do 16, and I think it's valuable because that would be what I would call just kind of a normal cone problem. You need to be able to do this on the quiz. Okay, I mean, that's about as close as I can come to telling you this is going to be on the quiz, right? Okay, when it comes to related rate problem. So on 16, it says this is the sand being dumped on a pile, so that means the cone's going to look like that. And it says in such a way that the radius is equal to the height. Now, it doesn't get much easier actually than that with that. Remember, what I said about the cone is any cone, as it grows, the radius and height are always going to stay in some ratio. If it's a big fat cone that's, that goes up, the radius may be way bigger than the height, maybe 4-to-1 ratio. Or you get a really tall skinny cone, the radius to height might be a 1-to-4 ratio, okay? But in this case, it's going to be more of a, I think that would make sense, square type cone. The radius and height are going to be similar in shape. Okay. Anyway, well, I guess that'd be more diameter and height. But anyway, somehow you're going to have that information. Okay. Now, the one we did with the tank the other day, it said that the radius was 4 and it said the height was 16. And so as the water fills up the tank, here's the height, here's the radius. So what you had is radius to height would be 4 to 16. And then, so you could just, so now you got radius equals 1/4 height. So somehow you'll be able to write an equation like this in a cone problem. Okay, somehow they're usually going to give you information where you can deal with that. Now, exception would be 23. Okay, and we'll talk about how 23 was different. All right, but so they tell you R equals H. So when they tell you here that V equals 1/3 pi R squared H, or when we know that the volume of a cone is that, now we can just make that substitution, and so all of a sudden this just becomes 1/3 pi H cubed. Okay, so we put the H in there. Now, the only thing that'll be different if it was R equals 2H or R equals 1/4 H or something like that, then when you put that in for R, you get a little messier fraction here, but it basically becomes the same kind of problem. Okay, so they tell me in 12 that there's 1,000 cubic feet of sand in the pile. Okay, so what would that be? What would I write that as? At the instant, there's 1,000 cubic feet. What's that? Volume. So they tell me V is 1,000. So they're always going to tell you some information, right? So V is 1,000. What else they tell you? V prime is 10. So the sand's getting dumped on there at 10 cubic feet per minute. So those are the two things they tell me. And they want to find what? H prime. Okay, so this is just what you do on these problems. And what can you find out? If there's any missing information, maybe we can get it, some other way. And we've done that with those problems, like we did that with the x squared plus y squared equal the ladder problem, right? When the ladder was 3 meters up the wall, we knew y was 3, but we didn't know x. Oh, but we knew x squared plus y squared equaled 36, so we plugged the 3 in for y, and we found the x, okay, so we can find that. So we got an equation right here we can do that with. I think we're going to have to, but let's do the derivative first. So we get v prime, bring the 3 down, so that would be just pi h squared h prime, right, like that. And now we're ready to plug stuff in. So for v prime, we can put a 10, and then we got a problem. What do we put in for h? We don't have anything. Okay, I'll come back to that. H prime is what we're trying to find. So what do we put in for H? Well, we don't have anything, but we do know V is 1,000. So what can I do with that? I can put that right there. Since I know at the instant when there's 1,000 cubic feet of sand in that pile, I should be able to figure out what the height is. It'd have been nice if they'd have just told me. A lot of times they would just say, how fast is the height changing when the height is 7? And then you put a 7 in for H, and that'd have been great. Okay, that would have been a little easy. Okay, but heck, they already made it easy with telling us that. So they told me V's 1,000, so I can do that. So I'm going to solve this. You got your calculator, you can solve that, it's fine. I need to solve that for h. Okay, if I don't use my calculator, it's going to be a mess, but so multiply by 3, divide by pi, and then the cube root of that. Okay, I would probably get myself a decimal for that with a bunch of decimal places or whatever. So that would be h. So that's going to go in there. And now you just have to solve for h prime. Okay, and again, use your calculator. So you got 10 equals, you can just type in solve, don't write this on your paper though, 10 equals pi, whatever this decimal was you got from that. And how do you do cube root on the calculator? There is a cube root button. Also, you can just go raise it to the 1/3 too, right? Okay, and so if there's a cube root button, find that too. But anyway, you get this decimal squared, and then, times x. Use x. Obviously, you don't have an h prime on your calculator, but whatever. Just call it x and just do a solve, right? Just do a solve for that, and let it do the work is fine, something like that. But anyway, solve it, and then the answer for h prime, according to my book, I guess anyway, is. Oh, Dad, they got a big mess of a weird thing. What do you get for, do you get decimal? 0.0328. Okay. All right. But that's pretty much a basic cone problem. Some information about the connects R and H because it's just nicer. Not that related rate problems, we need to get it down to one variable. We don't, right? We don't need to get it down to one variable. But if we didn't, we'd have had to do a product rule, and that kind of thing. And so, now on 12, did you have to do a product rule on 12? I think you did, didn't you? Sometimes you have to do a product rule. You were doing the area of a triangle. If you have area equals 1/2 base times height, and you're going to do the derivative of that, you got a prime, and I would connect the 1/2 with the b, but that's going to be 1/2 b prime, h left alone, plus 1/2 b, and then h prime. I mean, you're going to have that. And I think, didn't that happen on 12 for part B? Okay. And they told you that the base was, so b prime was 2, and the h prime, now what that says, the height is decreasing in such a way that the length of the hypotenuse remains 10. So that's like the ladder problem. So the hypotenuse was going to stay 10. Okay. Because you had this. Well, but when it says, but in B it says how, it says is the area increasing? So you had to there, didn't you? So, but for part B, but for part A, you wouldn't have to. Okay. And so the length. Well, I'm trying to think though. What? Is the area increasing? So this was decreasing, right? But did they tell you that amount, or you found it in part A? Oh yeah, you found it. I was going to say they didn't give you enough information, but you found h prime in part A. Okay, there you go. All right, and they told you b prime, so now you got that information. Okay, so but my point of saying this was sometimes you have to. So you could have done a product rule here, okay, and so it would have been okay. I mean, if I do that in black, if I was going to do it, I mean, I hesitate to even show you, but it never fails if somebody does it anyway. So if I do the derivative of this first part, the 1/3 pi just stays there. So I could bring that down. So I could have b prime is 2/3 pi r prime with the h left alone, plus 1/3 pi r squared left alone, and then the derivative of the h would be h prime. So I'd have something like this. But now think about what you'd have to plug in. You'd have to plug a 10 in here. Okay? You'd have to, what do you know? You're trying to find h prime. But since h is equal to r prime is going to equal h prime. Now maybe at this point you realize, I could just substitute. And maybe you do that. Okay, or maybe you're just stubborn and you don't want to do that at all. Well, then you start saying, well, I need to put something in for R, I need to put something in for H. Oh, I could put 1,000 in here. But then the problem becomes, how do you solve for both R and H right here? You know, if this is 1,000, so at some point along the way, you're going to have to probably make that substitution. Now, if they would have told you instead of V equals 1,000, if they would have told you like H equals 20, then you might have been okay. Because you could have plugged a 20 in for H, and then you just said, oh, R and H are the same. I'll plug a 20 in for R, right? So without substituting, you're kind of doing it anyway. And then all you'd have left is H primes and R primes, but then hopefully you'd have to say, oh, but they're the same. You know, so really at some point in time, you're in the cone problem, you pretty much have to make that substitution at some point. But on these problems, a lot of times you don't, but you might have to do the product. I just don't want you getting confused, because in the optimization, we do want to get it down to one variable, right? We do want to get it down to one variable. But this is not optimization, okay? It's just kind of a type of problem you need to do this. All right, let's talk about 23 first. Let me show you the trick to 23. And what's different about 23 in the cone is that they ask you what is the ratio of the height to the radius. In other words, they're looking for this. What is the ratio of the height to the radius? Which is a weird thing to ask for, something we haven't seen before. But otherwise, it's a basic cone problem. So if we get started with it, we got an inverted cone. The water's going to drain out at 10 cubic centimeters, so that's B prime, and that'd be negative because it's draining out. When the depth of the water, or H, is 8, the depth is decreasing, so H prime would be negative 2. So we got all this stuff that we kind of normally get. And we got this water, and it's draining out, okay? But they don't ask the question we're used to them asking. They ask us this. And so the problem with that becomes, what's difficult about that is we're not sure, you know, what do we plug where? Okay, in the cone problem before, we had some relationship between R and H, and we plug those in. Well, here's the secret to this, and this would have been, I could have given you this as a hint, but I wanted you to just think about it. If H and R, if they're asking us for the ratio of H to R, well, what we've said is that as a cone grows or shrinks, those stay in the same ratio. In other words, it's a constant. So let's call it K. Now, the beauty of that is what that allows us to do is to take what are variables and turn them into a constant, which is going to help us immensely when we come to do our derivative. Because now what I can do, since I don't know what that is, just call it K. Now, if I multiply over there by R and actually divide by K, and the reason I want to do that is because I'm used to getting the R out of there. So now I know R is equal to H over K. Now look what that does for me. I get 1/3 pi. I get H over K squared times H. That would make this H squared K squared. Now when I put this all together, I'm going to get pi on top. I'm going to get 3K squared on the bottom. And then I'm going to have H cubed. And see what I mean? Because what's nice about that now is K is a constant, not a variable. So there's not going to be a K prime, right? And so I can group the K over here with my other constants, and I now have got it down to one variable, which is what I want to do in this cone problem. So now when I do B prime, I bring down the 3, that'll cancel those 3's. I've got H squared, H prime. Well, now look. See those 3 things right there? I can put in -10, I can put in 8, I can put in -2, I can find K, and that's what I want. That's what I want, is K. Because K was the ratio of height to radius. And that's what they asked me. Okay? So the secret there was just let H over R equal some constant, and then go from there. Okay? So, probably don't have to worry about that for Friday, but what you do have to worry about is one like 16, a typical cone problem. But the connection, I mean, it's not that far away from just a typical cone problem, other than they just didn't tell you what that ratio is. Usually we're gonna know that ratio from the information. Okay? All right, now the swimming pool. Let's go ahead and do that, and then we'll give you some time to work today on just a variety of different problems. Okay, so in the swimming pool problem, there was two parts. One was when there was 2,000 cubic feet of water in the pool, and one when there was 3,000 cubic feet of water in the pool. Okay? Why does it matter? Why did they ask you two different ones? Part B, when there's 3,000 cubic feet, is when you're up here. Now, let's just talk about how to do this geometrically. The volume of this shape. Okay, well, the volume of this bottom shape is just going to be, if I call this, let's just call this A, and let's call this length across here B, just for the time being. Well, the volume of a triangular wedge is just 1/2. If that was a box, it's just half that. So it's 1/2, A times B, and then the width back here, which is 15. So it'd just be 15 halves AB. That would be this volume right here. Okay? Well, if you fill the bottom, the triangular wedge part, then that means the A would be 7, and the B would be 40. Okay? Well, if you take that, multiply that all out, I believe it's 2,100. I believe it's 2,100. Right? So, let's do part B first. Because why does it matter? Well, let's say, okay, so hose is pouring water in at a constant rate, and the pool starts filling up here in the beginning. Now, what's going to happen to the height as the water flows in? It's going to rise, but what about the rate that it's rising? Faster when? You said slower, Harish. What do you mean? The first bit of water that goes in, isn't it the pool going to fill pretty fast? But then as it starts spreading this way, right, more and more of the water is going to spread this way. So the height's going to go pretty fast in the beginning, and it's going to slow down. 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 And then what happens when it gets to here? Now it'll stay the same the rest of the time. So once it gets up here, it's going to be rising at the same rate the rest of the time. Okay? So for part B, once we get up to the 3,000, it doesn't really matter at that point whether it's 3,000 or whatever. If it's over 2,100 cubic feet, then it's going to be rising the same rate. So let's just do this. So let's see. I'm not even going to care about once the water's pouring in and it's up here. It's like this water doesn't even exist. It's like it's not even here. Doesn't matter. Okay. So I'm just going to look at that. The blue shape right there. So the volume of the blue shape is what right now? And we'll let that be H, okay, because the water's rising. So what would be the volume of that blue box? Length times width times height, which would be 15 times 40. What's 15 times 40? 600. Is that right? H. So wouldn't the volume of that be 600H? So now we just do the derivative. B prime equals 600H prime. Right? And what's B prime? What's B prime? Didn't they give it to us, 25 cubic feet per minute, right? So there's H prime right there, 25 over 600 feet per minute. Because we had cubic feet, we divide by square feet, because this was 15 times 40, so that was square feet, right? So that part of it, so part B is the easier part, okay, because it's up above there. And so it's just going to be a constant no matter where it is. Okay. So the bottom part is the trickier part. Okay, part A. So now we're down in here. Now it's actually 2,100, but it would be closer to the top. But anyway, I put it there. So now when the water's down here, so this is H because this is changing, but this is also changing here. We'll call that X. So that length is changing. See, so when the water's up here, as it rises, 15's not changing and the 40's not changing, so we can plug those numbers in right away. But here, this number's changing and this number's changing, but this number's not. So the 15 we can leave in. Okay, that number's not changing as the water rises. So now what's the volume of that? Well, it's a triangle, so it's 1/2 h times x times 15. So that'd be 15 halves h times x. That would be the volume of this triangular wedge. It's half a box. Okay? See, so now we have this same problem we have in the cone problem. So you might think, well, I could do a product rule. That'd be fine, and you probably could, but this is going to be a lot like the cone problem. You can do a product rule. You're going to have h's and x's, h primes and x primes, but none of our information in the problem, all we have is v prime is 25, and v is 2100, v is 2000, and we're trying to find h prime. So we don't have any information about x at all. And we don't, and so that's the problem. Well, again, just like with the cone, there's a similar triangle here. There's a similar triangle scenario right here with the red and the blue. So this is very much like the cone problem. In other words, h over x is proportional to what? 7 over 40. Here's 7. This is 7 right here because it's 10 all the way up here. So this is 7 and this is 40. So h over x is proportional to 7 over 40. So what that tells me is 7x equals 40h and x equals 47h. And then that allows me to plug that in over there. So I got 15 halves h and then 47's h. So from that standpoint, this is pretty similar to the cone. So that's 307's h squared, and then we can do our v prime. Right, and then we know v is 2000, so we know v prime is 25. I think I did this okay. I'm going too fast. I might have made a mistake. H, how are we going to get h? Well, we're going to take 2000, we're going to put it right there. We're going to take 2000, we're going to put it right there, and that's going to give us, then we can solve that for h. And then we will take that and put it down there. And then we'll get our h one. Okay? But again, so a lot of that's just calculation, so you can do all that. The key, though, was, first of all, understanding what the volume of a triangular wedge was. And then the second part is recognizing that there's a similar triangulation. Okay? So, same with optimization. Some problems are pretty easy and straightforward. Some are more difficult. What makes them more difficult? Well, it's really the same in each. Okay, what makes these more difficult is when you have trouble getting the equation set up, right? Getting the equation in terms of a single variable with the information. Okay, finding the equation. Once you get here, you just go through the steps. Okay, to get optimization with related rates, identifying the various rates, drawing and label, fine. But right here, write an equation that relates to various amounts, and that was what was tricky in that one. Okay, so probably on the quiz, most of them, many of them, if you've been spending time with the homework and then we practice some more in the next couple of days, are going to be similar to things you've seen in the homework. So they should be, ones you should be able to set up. Most of them are not going to be as challenging as like the swimming pool or that 23. Okay, but I'm going to let you have some work time here today on a new packet. This packet is from another book. I call it Anton, just because, again, that's the author of the book I took it from. So, okay. So now this one, it's kind of interesting in this particular book is they're not even in the same chapter where they do these two things, which is kind of bizarre. So when you look, this says exercise 4.6, and then it says exercise 6.2. So they were like a different thing. But so the first couple pages I think are related rate kind of problems, and then the next a couple pages are optimization. Now it should be obvious when you read it which type of problem it is. So circle problems basically is your homework. Tomorrow we'll review some of each of the types, answer questions, and give you a few more to practice with. I think I've got the Anton answers also. I'll probably print that out and I'll have it out here if you want to look at it while you're working, if you want to check as you go. Also put these Anton ones online.
We get some mistake tens.
Well, I'll try to find some, yeah.